Hi everybody, welcome back to Chem 140. It is Tuesday of week 4, and how did we get here already? Like, I feel like I blinked and yesterday was like the first day of class where I was playing Mega Man or something. And then all of a sudden we're in mid-October. What does that mean for you? It means that we are on Unit 6 of 16. And also there's an exam next week. Dun, dun, dun. If I had more time prepared, I would have queued a sound effect for that, but no exam this week, just quiz number 2 that's due tonight. Deadline is tomorrow for when it closes, but try and do it tonight so you don't forget about it. That's how the due dates work. You're going to get another quiz number 3 for units 4, 5, and 6. However, there is going to be a slight change for when it's due. It's not going to be due a week from today. It's going to be due on, like, Sunday or something, and then it will close Monday so that on Tuesday I can release it so you can see the answers before the exam on Friday. Maybe it'll close Monday or something like that. It won't be a week. It'll be slightly less than that so that you have enough time to review the answers. And then I think quiz number 4 is Unit 7 and 8, which there will be issues with that quiz being posted before the exam. So I will figure something out, and we'll talk about that when we get there. But for now, we're going to finish up Chapter 6. Chapter 6 was all about matter, how we categorize it, how we define it, how we do stuff with it. And what we're going to do now is we're going to look at mixtures, because everything around you is a mixture, to some extent. If you drink water from your tap, assuming that you're in Everett, you're drinking a mixture. Actually, that's just a joke. You're assuming you're anywhere. You're technically drinking a mixture, because in order for you to have something that was pure, like, oops, my slide didn't advance there. Like the water shown on this slide, every single molecule in there would need to be water. But that's not realistic, right? There's got to be one atom of lead in there, yeah? One molecule of, like, I don't know, some sort of antidepressant or whatever. All your medication ends up in the water, by the way, because of how we recycle water. Yes, you are drinking recycled water. That's what purification is for. But it's water, right? Chemically, H2O, doesn't matter if it's been through only your body or through 70,000 people's bodies, which all water pretty much has. Isn't that nice to think about? This water's been consumed by someone else before. I'll drink to that. But it's true. For our purposes, when we consider something to be pure, I'm going to put it in quotes, but in reality we don't need to do that. I'm going to say that something that is pure is almost completely one substance. And by that I mean like 99% or more. So, if you buy chemicals from a chemical supplier, and you probably won't run into this until you start doing science classes where we hand you bottles of reagents and say, here you go, this is what you're going to use for the lab today. If you read the label, depending on the purity of the substance, it will be listed on the label. It'll say greater than 99.99% pure. Depending on your application, that's important. For the most part, everything that we encounter is going to be a mixture. So, we're working with a theoretically pure substance and the ubiquitous mixtures that are everywhere around us. So, we're going to define any sample that has only one substance, and that one substance can be described by one unique chemical formula. We're going to call that a pure substance. In other words, if you have a container or bottle or whatever, and I point at it and say, what's in the bottle? And you can describe it with just one formula or elemental symbol, it's a pure substance. Isn't it dangerous to drink really pure water? I've heard that. It's dangerous to drink too much water. That might be where that gets conflated. I feel like this is along the lines of urban legend. The drink really pure water. Because what you're drinking in as water is essentially pure. Like if you buy a bottle of distilled water from Fred Meyer, for our purposes, it's pure. Is it dangerous to breathe pure oxygen? Yes, that one I know for sure. Because too much oxygen in your body causes it to accelerate certain processes, and also oxygen is really good at oxidizing stuff, and that can be bad. We actually want to control the rate at which oxygen enters our body. And fortunately, the atmosphere has done that for us. So those are pure substances. You could have pure oxygen, which would be in the gas cylinder. There would only be O2. No other filler gas would be present, at least not in an appreciable amount. Now, any other substance that has two or more things in it, we're going to designate as a mixture. And so a great example of a mixture would be air. Air is a mixture. You can't breathe pure air. Don't you age faster? I feel like that's one way to describe it, but I think that aging might be like too complex of a mechanism to really agree with that statement just like straight up as written. Like the whole process of aging is that like you are having like side reactions that oxidize things are happening, I think, and then systems start to break. This is just the inevitable fate of all chemistry, really, is that eventually whatever reaction you're studying decomposes or whatever. So I guess my answer to that question would be yes, question mark? I think there's a big question mark there, though. All right, those are our two categories, pure substances and mixtures. I'm going to make this little chart here for you. And remember, the first question that you're going to ask when you answer any question about categorizing matter is there only one thing in the bottle? And if the answer is yes, you are looking at a pure substance. And if your answer is no, you're looking at a mixture. Now, we are going to separate these into their own categories as well. So that's why there's a lot of space available at the bottom here. We're going to define pure substances and then split that into two categories for two different things that fit that description, and then do the same thing for mixtures. So let's start with pure substances here. We're going to look at any pure substance that contains either only one type of atom in it or multiple types of atoms in it. So on the screen here, actually, let's just put the element up here first. We're going to define an element as something that contains only one type of atom. Now, what are the types of atoms that are available? If I could get my mouse to move over here. The way that I have my desk arranged, I have my mouse on a cord that's like wrapped around a bunch of things. Really, what I need to do is I need to just do this. Oh, can I do this? Hold on. Let's see if this works. Okay, that's much better. Okay. I had it wrapped around my monitor because it was convenient for where I normally have the mouse, but when I do this, not so great. So what am I looking at? I'm looking at ptable.com. So that I can then copy the link and paste it in the chat. So this page right here, we're going to use this a lot. This is ptable. And I guess I should capture it, shouldn't I? Window capture, periodic table. Boop. That's a little small, but We don't need all the products at the bottom. We just need the table. We actually don't really need all that information on the side. All right. So on your screen, this is P table. Apparently it's a night mode now, which is kind of cool. And what it lists are all of the elements that are known to humanity. And I had to get my periodic table here because I can't read this. It's in a capture window. It's real tiny on my screen. But you can see here all of the different elements that are all of the different atoms that exist. Now, we're going to define what an atom is in Unit 7. That's going to be later today in the second half. But for now, just think of an atom as little entities that have names. Some of the atoms are named hydrogen, other atoms are named oxygen, other atoms are named carbon, other atoms are named molybdenum, and so on and so forth. If you have only one type of atom in your substance that you are examining, we're going to call it an element. For instance, diamond contains only one type of atom. It is just carbon atoms over and over and over and over and over. And if you arrange them in a very specific way, you get diamond. If you arrange them in a very different but also specific way, you get graphite. And if you arrange it in a third specific different way, you get Buckminster fullerene. These are all examples of elements of carbon that are just different rearrangements of atoms which have different properties. You've probably never heard of Buckminster fullerene. You can look it up. It's carbon. It's a ball of carbon with 60 atoms. Graphite, you have heard of. That's pencil lead or coal. And you may have heard of things like graphene and carbon nanotubes. Those are other forms of only carbon, which they're very cool in their own right to study. Way beyond the scope of this class here. We got to learn a lot more before we can talk about graphene and carbon nanotubes. That's okay. On the bottom here, I have a salt shaker. You might have heard of table salt as named sodium chloride. And the reason for that is because it contains those two elements, sodium and chlorine. If there are more than one type of atom, oops, sorry about that, clicked the wrong thing. If there's more than one type of atom present, then we're going to call it a compound. So compounds contain repeating substances, but those substances themselves contain two or more molecules. For example, water would be a compound. It would be H2O. You have a molecule that contains an O and two H's, and then you copy and paste that molecule over and over and over and over and over to make the substance. I'm going to show you a picture of what that looks like at the molecular level at the end of this discussion. So there's pure substances. We have elements and compounds. So when you go back to your chart here, oops, don't know why I did that. When you go back to your chart here, and I'm going to expand this chart on a future slide. When you have determined that your substance is pure, you are then going to further subcategorize that as either element or compound. That's basically where we're going here. All right, now we're going to do the same thing for mixtures. We're going to look at two different types of mixtures. Now, by looking at the pictures here, and I probably need another color because this is going to match the ketchup, so let's do blue. If I were to take any sample of the ketchup, either like from the side here, or just on the top, or even along the bottom of the container, all of these samples would be indistinguishable, right? Oh, I ran out of words. I ran out of room here, didn't I? Let's see here. Indistinguishable. There we go, I made it. I could keep writing over here on my screen. It will let me, but it goes off of what you can see, so I had to be careful about that. So if you can take a mixture, of which ketchup is a mixture, you can look at the side of the bottle and it will list multiple things. And all of those samples that you take from the mixture are indistinguishable. In other words, they're all virtually identical as far as your senses can tell. We're going to call that a homogeneous mixture. In a homogeneous mixture, all the portions are identical, at least as far as we can tell. So an example of this would be like air. If you take a deep breath, and then you breathe out, and then you take a second deep breath, your lungs won't be able to tell the difference between your two breaths, because the air is a homogeneous mixture. All gases end up being homogeneous mixtures, it turns out. At least if you give them a little bit of time to mix. Now, if you pass gas or fart or whatever, have a flatulence attack, I'm trying to find as many synonyms as I can just to dwell uncomfortably on this topic as long as possible. Like, you might smell that and then be like, oh, that smells awful. And then eventually the smell goes away because it fades out, right? It mixes with the air. During that time period, every breath you would take would not be identical. My food example that I have here is the salad dressing. If I take a sample from the top here, I get a bunch of oil. But if I take a sample from the bottom, I get all the herbs and the good stuff. And even if you mix the salad dressing together, it will eventually separate apart because part of the salad dressing is oil and the other part of the salad dressing is water-based, right? If you have any Italian salad dressing in your fridge and you go and grab the bottle right now, providing someone has not used it recently, it will have separated into two layers, and you have to shake it, right, before you use it. Otherwise, you just get the oil part, which may not be what you want. If you can describe a mixture in this way, i.e., every portion is not identical, we're going to call it a heterogeneous mixture. Now, you've heard the terms homo and hetero before. We use this as slang for people's sexuality, right? Someone who's homosexual, like someone of the same sex. So homo, the term homo must just mean same, right? Hetero is somebody who likes somebody of the opposite sex. That means hetero must just mean different. And so that's how you know. So anytime you see homo or hetero, you automatically know more or less what it's trying to describe by that term. So homogeneous just means same, and then geneous means composition. And then hetero just means different. See, we can be topical and have current cultural stuff in chemistry too. Now, what happens when you get to the point where you're like, well, I don't know if it's all the same. So, for instance, if I said, what would you categorize blood as? Now, if you look at blood, like when you get your blood drawn in a vial, it looks pretty homogeneous, right? But if you put it in a centrifuge, all the plasma will separate out. The plasma will separate up to the top, and the cells will coalesce down towards the bottom. And then it looks very heterogeneous, right? So, how do you describe something like that? There is a midpoint where you get to a region where it's sort of between a homogeneous and a heterogeneous mixture. And my advice for you is that the best that you can do is just use your senses in order to distinguish them the best that you can, and avoid circumstances where, like, you subject a substance to extreme conditions. So, for example, we would not take a gas and pressurize it to the point where it would start to boil, or to where it would start to liquefy, and then say, "Ha! It's a heterogeneous mixture because there's liquid and gas present." We don't want to do that. So just at the state that you observe it, like maybe a little gentle mix or whatever, if it seems like it's going to stay heterogeneous and not become homogeneous, that's the answer that you're looking for. And so ketchup is a good example if you've left it in a bottle. Now, in order for you to answer that question, the problem that I would have to give you would be ketchup but left out so that that thin little layer forms on top. Now, if I just said ketchup, what I am assuming is that it's well mixed, that you shake in the bottle and you went and you put it on your hot dog or your French fries or whatever. That's the ketchup I'm talking about. And so you would answer that as homogeneous mixture. Because that's the intended state, right? You don't eat ketchup by getting that little bit of liquid. You don't eat that, right? Like, that's not the part where you go, that's the best part. No, nobody says that, right? You shake up the ketchup so that everything's mixed well. And that's what you eat. I'm saying this as if I eat ketchup. I actually hate ketchup. I put sriracha on everything instead. But same thing. Sriracha does the same thing. Like, there's a little thin layer on the top. So you shake it real well, and then we call it homogeneous. So I'm going to ask you questions on quiz number 3 about homogeneous versus heterogeneous. And what you will have to do is you will have to look at it and interpret, okay, what's the intended state of this? For instance, if I gave you water with sand in it, you can imagine like, oh, okay, I have sandy water. It's kind of like floating around. But there's probably not going to be the same amount of sand everywhere because it likes to settle out to the bottom. So there will be more sand at the bottom than the top. Therefore, heterogeneous mixture. Not every sample has the same amount of sand. They're not all identical. If I gave you something like carbonated beverage, the intent is that every sip should be the same, right? So therefore, it should be homogeneous, and that'd be the intended answer. All right. So there's our chart. This is the finished chart. Remember that you're going to start all of your inquiries up here. That was the worst star I could ever draw, I guess, but that's okay. You're going to ask yourself, is there only one thing in the bottle? And if the answer is yes, you have pure substance, which you can then separate into an element or a compound. If the answer is no, there are multiple things in the bottle, then you have a mixture. And then you just examine, are all the portions indistinguishable, yes or no? Here's a picture version of all this from the first textbook I ever had, back when I had to scan pictures. Like, ooh, I was so new, I didn't even think to look on Google for images. No, I just had the textbook handy, and I really like this picture, so I kept it. You can see at the molecular or atomic level what these things look like. So you can see that copper, there's only one type of copper element. It's this brown sphere here. This is copper. Whereas this cluster that I'm circling right here, this is sugar or glucose. Should be C10H22O11. Here you have oil and water. The water is down here. And then this is what oil looks like. And then finally over here with the soft drink, you have a bunch of stuff. So this guy's CO2. This is H2O. I want to say that that's caffeine. This is phosphoric acid. And so on. So hopefully the visual examples help you get a sort of idea of what atoms look like, because that's what we're going to talk about in the next section. All right, so I have some practice for you. I'm going to number the problems again. And what I want you to do is I want you to tell me which category each of these substances fall into. Now, when I ask you for a category, what I'm asking you for... Oh, there we go. What I'm asking you for is to give me one of these things. Okay? So it's either going to be an element or it's going to be a compound, or it's going to be a homogeneous mixture, or it's going to be a heterogeneous mixture. So you have to do the sort of pachinko thing where you fall into the correct spot to figure out what the answer is for each problem, okay? So work your way down the chart by reading these descriptions. Use your senses and your knowledge of what these things are, but in some cases, I will try and describe them for you. So, for example, in the second problem, I have a parentheses here. Anytime I write parentheses, the intent is the only thing in the bottle is the thing in parentheses. Okay? So, nail polish remover has only acetone in it, and there's its formula. What does that categorize it as, for example? And then, very important, make sure you answer number 5 completely. I'll give you about 5 or 6 minutes to go over these answers in the chat. Good luck. We're all counting on you. All right, one more minute and we'll go over the answers. All right, let's go over the answers here. All right, for number one, if you have a can of Red Bull, and I really should have just grabbed a picture of this. So Red Bull label. Let me try and find. Is this going to work? I mean, it would. Oh, there we go. Okay. So let me see here. Where is. That's what I want. Okay. All right. So if I do this. All right. So here's the label for Red Bull. And you can see down at the bottom. Well, you can kind of see. Down at the bottom where it says ingredients. If there's more than one ingredient, it has to be a mixture by definition, right? So, if you aren't sure of something and it's a substance that's generally for like human consumption, consult the ingredients. And then that'll tell you right away. So, this must be some sort of mixture. Now, what's the intended state of the mixture? Is it intended that it separates out and you have a different drinking experience at the start and at the end? Probably not, right? The whole thing should taste the same. So this must be a homogeneous mixture. In fact, virtually all beverages are, if it's just a liquid. Now, if you have a liquid with ice in it, then some of your drink would have ice, and other parts of your drink would have no ice in it. If you could just like take regions of the drink and circle them, and then it'd be heterogeneous because not all the portions are the same. For number two, oops, the chat fell off the screen. Hold on. For number two, if nail polish remover is 100% acetone, now it's not. Usually it's a mixture of water and acetone, but let's assume for the sake of this problem that it's just acetone, and this is its formula, that's multiple atoms in the formula of the substance. So we would call that a compound. All right. How about poorly mixed gravel? I have some sand, some rock, some salt. I just threw it in the bucket and then went stir. And that was it. Well, any scoop you take at the top is going to have whatever the last thing you put in is, and whatever scoop you take from the bottom is going to have whatever the first thing you put in is, if you don't stir it well. So this is going to be a heterogeneous mixture. All right, what about a cylinder with nitrogen gas? Well, if we go back to P table, and get rid of the Red Bull here, and P table, boop, and we look at the periodic table and we find nitrogen. There it is right there. There's our nitrogen. Nitrogen gas is actually N2, which we'll learn about a little bit later. But because that's the only element listed, we can call it that. It's an element. All right. For number 5, pizza. Is every bite of the pizza going to be identical? No, because you have the crust, right? And versus the middle. The middle tastes different from the crust. The crust is more bread and doughy. And the middle is more cheese and sauce and ingredientsy. So, pizza must be a heterogeneous mixture. Now, what's the best pizza? The correct answer was Zeke's Pizza. However, Zeke's Pizza is rather expensive, so I understand if students have never gone there. But you should. It's really, really freaking good. And, like, I order the most basic pizza at Zeke's. I get the Dragon, which is pepperoni, sausage, and jalapeno. And a bunch of garlic. And it's so good. Mod Pizza is good for fast food pizza. Like, it's cheaper pizza, but it's good for the price. But I mean, I will never turn down Zeke's Pizza. So that's my recommendation for you. Iron metal, the only element listed in the iron metal was iron, which is an element. Now, steel metal, steel is kind of a weird one. How is steel made? Steel is made by adding in all of the elements into, like, say, a mold. And then you heat the heck out of it until it's a liquid, right? You get molten metal. And you pour into the mold your steel mixture. And then you let it cool. So, because there isn't really a formula in terms of a chemical formula for steel, it turns out, it's just a mixture of like 97% iron and 3% this and 1% that, and that adds up to more than 100, but that's okay. It turns out that steel is a mixture. Oops, I drew off the screen, or I was holding a button or something. But what type of mixture is it? Well, if every part of the steel was different, that'd be kind of weird, right? You could only build with, like, the left side of the steel, because that's the strong side and the other side is weak. That doesn't make any sense. So steel is actually a homogeneous mixture. So this is sort of a trick question for me to teach you this. But steel is what's known as an alloy. And an alloy is a mixture of metals. And all alloys are homogeneous mixtures. Some examples of alloys would be things like bronze, or brass, or electrum. Stainless steel, pewter. These are all examples of alloys. They are mixtures of metal that are made by heating two metals in the presence of each other. If you've ever read anything about the Bronze Age and how bronze was discovered, where they used to use copper weapons, and copper is not very great as a metal because it's very soft. But by adding tin to it, it turns out that the result is much, much more durable. And that's how the Bronze Age started, was people making bronze arms and armor. Because somebody accidentally dropped some tin, I guess, into the copper when they were making copper stuff, and then the result was better. Is each metal a separate substance? In an alloy, not necessarily, though if you zoom into the atomic level, it would look kind of like you had a it'd be... how do I want to describe this without drawing a picture? I know. Let's draw a picture. So it would be kind of like this. So what an alloy looks like at the molecular level would be, and this should actually work today because I rebooted my computer. So if this was my alloy where all my atoms were crystallized together, we'll assume that I'm drawing a regular solid because I'm not perfect at this. What an alloy would look like would be something like this. So the purple ones would be the small substance that you've put in here. And for whatever reason, just having these present makes the mixture stronger. So the elements exist separately in the mixture, but the end result is that they're all bonded together in a specific way that just happens to make the metal more durable or more heat resistant or whatever property the substance has. All right, I think that's the end of chapter 6, more or less. Yeah, when we come back from the break, we're going to talk about symbols and formulas, which is just, here's what we write when we talk about various atoms or molecules or whatever. So, like, if I say hydrogen, you write H. If I say oxygen, you write O. If I say xenon, you write Xe. That sort of thing. So, we'll do all that after the break, since it's about that time. We'll put the timer up on the board. We'll do this. And then oops. Every time it asks me, new updates are available. Never update. We're going to put on one of the best tracks from Donkey Kong Country 2, and maybe one of the best tracks in like video game history here. So I hope you enjoy it. Alright, we're back. Alright, for the next section, what we're going to talk about are how to properly write and notate various formulas that we're going to encounter in chemistry. Oh, we're also going to meow. Hi. Meow. No, he doesn't want to say anything anymore. Alright. This is a video that is definitely going to get me copyright struck, so I'm not going to do this. This is not a Rickroll. The link that I'm going to post for you guys here, if it opens, I might have to actually do it this way. Actually, what I'll do is the audio is muted, so you won't actually hear what comes up here. Okay. Let's see here. What I can do is I can put this on the screen. You may have seen this video before, and so I'm going to have to just have this as a link for you. Oops. We gotta make this smaller here. Alright. If you've seen the video, History of the Entire World, I guess, and so let me share this with you. Oops. That obviously doesn't work. We'll paste that in the chat here. Oh, and you don't need to see that anymore. But this is a 20-minute joke video of the world from the Big Bang all the way up through humanity filling the ocean with plastic, basically. So, like, the first 5 or so minutes are chemistry and physics and biology, and then it starts doing history. It's worth watching the whole thing because it's very memeable. If you have Steve Powell as an instructor at any point, if you say the words, "You can make a religion out of this," which is something in the video, he'll yell at you, "No, don't!" Because it's a meme. And, like, we quote this back and forth all the time. But there's a really good description of where the elements came from. And according to this chart here, which is the elemental composition of the sun, this is a rough approximation of the elemental composition of the universe, shown here. Most of the matter in the sun is hydrogen. It's just protons flying around. A smaller chunk of that is helium. And then everything else is all the little teeniest, tiniest sliver, which you can't even see. We have to zoom it in here. Is all the other elements. And presumably this diagram keeps going, but this is just the slide that I pilfered this picture from. Is that there's like another little sliver here, which is all the other elements. And so the gist is that at the start of the universe, we just had protons and electrons flying around. And then we started pressing them together to get other elements in giant explosions. Or space dust, as the video that I linked to you shows you. So, where did all this matter come from? Well, we started with fundamental pieces, which we'll talk about in Unit 7 later in today's lecture. And then we just sort of crammed them together in supernova and stuff like that. And the result is that we got 118 different types of matter that we categorized on the periodic table, which is where p-table comes in. Now, most of the symbology that is used for the periodic table is sort of a, well, duh symbology. We take the first letter, or the first 2 letters, or sometimes the first and the third letter. It's just sort of whatever people felt like, I guess, when they were coming up with these names. So on the left, I have some examples there. Down here at the bottom, I have some examples of element symbols that do not make sense based on their current name. And the reason for that is because they were discovered by other societies or civilizations, and we adopted their name. For example, iron in Latin is known as ferrum. And because the Romans discovered iron more or less first, and that's the record that we use or think of where it comes from. That's the name that we use. Sodium, same thing. Natrium is the Latin word for sodium. In German, the word tungsten translates as wolfram, and that's where W is used. So the symbols sometimes go with languages that are not English. Most of them, however, are from the English name. Now, these symbols are universal. What that means is that this is not the letter capital X with a letter lowercase e after it. It is a symbol in the same way as this is a symbol. If I were to draw this like this, where I drew them both lowercase, or I drew them both capital, or something like that. So if I did this, these are not the same, and this one is wrong. That's the same in terms of me saying, oh, okay, well, I'm just going to make it slightly smaller. Or I'm going to make it upside down, or something like that. No, you're not. When you write chemical symbols, you must write them as shown on the periodic table. The first letter is capital. The second letter is lowercase. If you're writing it out by hand and you write in upper cap or lower caps, which is like, I write like this, where the first letter is like bigger or something like that, you can do that. That's fine with your handwriting. But when you write elemental symbols, the second letter must be lowercase. If it's not, it gets marked wrong. And if you do like that on Canvas, it will mark it wrong too. Okay? So be mindful of that. You want to make sure that you are writing the symbols out correctly. The next thing you want to be able to do is find all of these elements on the periodic table and then note where the tricky parts are. What do I mean by tricky parts? What I mean is if I ask you to look for potassium and you go over here and you're like, well, here it is. That's not potassium, actually. I don't know where that last line went, actually. That's phosphorus. Potassium's actually over here. It has a Latin-sounding name. All the ones that end up in Latin have the weird things going on. If I asked you where tin was, you might say, oh, well, I'm just going to look for Ti. There it is. Oh, that's titanium. Tin is actually right there. It's SN or stannum. So just be mindful of that. There are tons of elements that start with C. If you're looking for chlorine, there's an H, an L, an O, an R, an I, an N, and an E in chlorine, and most of those appear on the periodic table next to the letter C. Turns out Cl is chlorine, which I drew a red line over, unfortunately, even though chlorine is spelt CHLORINE. We use the first and the third letter. Why? Who the fuck knows? It's chemists, right? Chemists are dumb when it comes to making up stuff, and we're going to learn that as we go through the quarter. You're going to be like, why the hell did they choose this? And that's going to be my answer. Chemists are dumb. They thought this was a good idea. It turns out not so much. So just keep that in mind. You'll become acclimated to this as you just get experience with and practice at looking at the periodic tables. So don't worry too much, but resist your first instinct to go, oh, there it is, and point at the first letter that sort of matches what you are looking for. P-table has all of the names of the elements there. Just make sure you're looking at those when you're writing down the symbol. Now, when you write out a formula, the way that you do that is to just simply list all of the elements one after another. There is an order to it. We're going to talk about the order later in 161. For now, it's not super important. For example, if I want to describe water, I know that water has 2 hydrogens in it and 1 oxygen atom. I didn't underline the numbers. That's kind of important. So what I would do is I would say, okay, 2 H's, H. I'm going to put a 2. And then there's only 1 O, so I'm going to just write O with no number. Numbers are always subscripts. This is an issue that we run into when trying to do things on a computer or whatnot. You cannot write subscripts using a computer or Google Sheets. It's not a word processor. You can do that if you're using Microsoft Word or some equivalent, Google Docs or something like that. So when you're writing things down, make sure you're writing the formula with the subscript correctly. When you're typing it into Google Sheets, just type a number. Don't worry about it. All right. So let's do an example here. I'm going to write the formula for ammonia. Ammonia has 1 nitrogen and 3 hydrogen atoms. So what would you write on your paper? I'll give you a second to jot it down while I tend to... There's a cat somewhere that I can hear. Maya, where are you? Oh, there she was. She was in the hallway. Maya, do you want to tell them what the formula for ammonia is? Oops. What is it? There you go. Very good. Maya says that it's NH3. So we'll write that. NH3. There you go. Good job, Maya. 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 Hi. Everyone loves you, Maya. All right. Now, note again that we don't do this. If there's ever 1 of an atom in a formula, you don't write the 1 in there. And the reason for that is just to make the formula a little bit shorter and more compact. The 1 is implied. Oh, you're a floof. Oh, she ran away. She's very mysterious. Like, I'll turn around and she'll just be gone. And then I'll turn around again and she'll be right back there. She's like the quantum Steph in Outer Wilds. I have a quantum cat. I did not teach my cat chemistry, unfortunately. I am trying to teach her to say hello. And that's going remarkably well, because whenever she meows at me, I say hello. And so our conversations are literally meow, hello, meow, hello, meow, hello. And eventually she'll be like, meow, meow. And then I'll get really excited because it sort of sounds like hello. The other cat I have doesn't want to talk at all unless he wants you to hug him. All right. Writing in upper or lower caps or whatever this is called. Don't do this. This is also wrong. If you do this on paper, everybody will cross it out and circle it and tell you that's not right. Just saving you a lot of heartache later. Every instructor in the department will nail you on that. So just be very careful. Make sure you're writing the formulas correctly. Now, something that comes up is that when you write a formula, you might have specific ions, like the polyatomic ions that I talked about at the beginning of the chapter. Those tend to stick together, and what we end up doing is if we have polyatomic ions, we end up putting parentheses around them and then putting a number after the parentheses. And what that means is that there are 3 of each of hydrogen and hydrogen. So you can think of it like multiplication. If you see a subscript after parentheses, what that's saying is that anything in the parentheses is going to be multiplied by 3. Now, if you had something like this, then that would be 2 nitrogen and 4 oxygen are present there because I have 2 NO2 clusters. You gotta think of this as multiplication using like blocks or stuff like that when you were little and they were trying to teach you how to multiply things. And you do 2 times 3, so you'd get 2 piles of 3 blocks or whatever. Same thing. Same thing you're doing here. All right. On the board here, I have the example for magnesium hydroxide. We're going to talk more about polyatomic ions later, but just so the parentheses don't surprise you, this is the proper way to write the formula. We would not write it like this. Now, this is true for ionic compounds, which we'll get into in units 8 and 9. Sometimes when we talk about organic compounds, you'll see weird situations where it's like, oh, why didn't they compress this? Why did they write it out all weird? And we'll talk about that more when we get to structural formulas and stuff. All right, so what I want you to do is I want you to interpret the following formulas here. So I have a bunch of parentheses present, and what I want you to do is, for each of the formulas, I want you to index how many of each atom are present. So in the first formula, how many carbon are there, how many hydrogen, how many nitrogen, etc. Like, obviously, duh, the first one, you just count the numbers and you're done. But the second one's a little more tricky. And then the third one is that expanded notation where it's like, why didn't they just combine all the H's and C's and O's? And we'll talk about that. So go ahead and count all of these up. And we'll go over the answers in about 2 or 3 minutes. Oops, I just realized that, like, yeah. Google will do that when it thinks your responses are spam. I'm going to give one more minute, and then we'll go over the answers. All right, let's go over the answer. Stylus. Uh-oh, where'd it go? There it is. All right, for the first one, let's change this color. 18 carbon, 21 hydrogen, 1 nitrogen, and 3 oxygen. Kind of like duh, right? So, that's great. For the next one, it's a little less obvious. There are 10 calcium, of course, but how many phosphorus are there? Well, I've got 6 clusters of this, and in each cluster is 1, so there's 6. How many oxygen are there? And you might think, oh, okay, well, it's just 6 times 4 is 24, but then you got to count these over here, too. And then the H is just 2. So it can be tricky. You have to be careful about counting these. Make sure that you get all of them. Down here at the vinegar, I've got 2 carbon, 4 hydrogen, and O, 2 oxygen. You may actually see vinegar is written like this. Or even weirder, you might see it written like this. And there are special reasons for both. There's also a special reason for why it's written like this. And it turns out that when you're writing formulas for specific molecules, there really isn't a convention because people just did whatever the fuck they wanted to at first. And those examples got grandfathered in. And vinegar is kind of one of those molecules. Vinegar is one of the simplest molecules. It's also acetic acid. And because of that, it has a common name. It's called vinegar, right? But it is used in various applications, and these formulas are useful depending on that application. For example, this one right here, this is useful for if you're working with acids and bases. Writing it out like that is useful. This is more of an organic type structure, which tells you the order that the molecules, or not the molecules, but the atoms within the molecule appear, and so on. So there's different reasons why we would want to write stuff different ways, in other words. Down here we got platinum. There's 1 platinum. There's 2 chlorine. And then for the ammonia part, we just multiply this in. There's 2 nitrogen and 6 hydrogen. Okay. So make sure you're multiplying when you do parentheses, because that's what that means. All right. If you have any questions, let me know. I believe that's it for Unit 6. Yep, there we go. Oh, we gotta unmute this guy. We'll just do that again. Oh, okay. Or it could just give me the end of it. There, I'll just do that. Alright. Give me a second. I need to boot up Unit 7. So the screen's going to go blank for just a bit. Open. There we go. Okay, Unit 7. Can close Unit 6. And boop, should appear. There it is. All right. Unit 7 is all about what is an atom. Now, there is a little bit of math towards the end. We're going to do addition and multiplication. Nothing major, though. But for this unit, we are going to talk about what atoms are and how to represent them in terms of like a physical structure. So you're going to be able to draw a model of the atom. And then you're going to be able to draw what a molecule would look like, and so on. And then in a later chapter, we're going to talk about bonding, where we bond stuff together. And you can see how atoms connect to each other to form larger, more complex structures that we can then use for various applications. So let's talk about what atoms are. For this, we're going to need to do a thought experiment where we imagine a sample of copper. And we'll just draw that as a square here. So there's my copper. I don't know why it's blue. And what I'm going to do is I'm going to say cut the copper sheet in half. Boop. There you go. And I'm going to ask you to do that again. Boop. And again. Boop. And again and again and again and again. Boop, 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 boop. Now, at some point, you would get down to the tiniest possible piece that you could still call copper. If you cut this in half, the result would not be copper anymore. So there is a limit, a physical limit, if you will, of the action of cutting and subdividing this sheet. That physical limit is where you approach the atom. So an atom is just basically the tiniest possible piece of this lump of copper, or the sheet of copper in this case, that we can still call copper. If I break that into pieces, those pieces are going to be the parts of the atom, like the protons and the neutrons and the electrons, which we're going to discuss in a little bit here. Sorry, I had to cough. Had to hit mute there for a second. So here's another example of that. So I have gold on the left. This is what a lump of gold looks like. It crystallizes in sort of this bizarre flaky pattern. But if you put it under an electron microscope and you zoom way far in, you actually see the individual atoms of gold. It's not high resolution because atoms are very, very tiny. In fact, each of those atoms is on the order of 10 to the minus 22 grams of matter. Oh, excuse me, that's real small. On the board, I have a approximation of the number of atoms that would be needed to go into a paperclip. I did that calculation when I wrote this slide, and you can do that calculation too when we get to unit like 13 or so. But the number of atoms I calculated is roughly 10 to the 21 atoms. That's a lot of atoms. So they're real small. Atoms are unfathomably tiny. I must have clicked somewhere else. There we go. Let's look at a picture of an atom in terms of the nucleus, which is the solid part of the atom. We're going to describe that in a little bit more detail. And the electron cloud. Now, this picture is not to scale. In fact, if this diagram was drawn to scale, and that's like 1 centimeter. I have a ruler here. Let's see how big this is. So if this is 1 centimeter on my screen, it's more like 2/3 of a centimeter. So we'll round up to, we'll say it's 1 centimeter. If it's 1 centimeter on your screen, then that blue cloud should be 1 times 10 to the 5 centimeters away, or roughly 100 meters away. So that would be outside of your apartment or house, and probably a ways down the road, 100 meters. That's quite a distance. So, in other words, this diagram is way smaller than it should be. And if the only solid part of our atom is that red dot in the middle, the majority of an atom, by far, 99.99%, is just empty. It's just empty space. And because you're made of atoms, the same is true for you too, as is everything else around you. Kind of a shocker. Did you imagine that today I'd be telling you that you are a 99.9% void? As is everything else in the universe? Except for neutron stars. They're packed pretty tightly. But, yeah. So if someone calls you an airhead, don't take offense to it. Say the correct term is spacehead, dumbass. Or something like that. You have my permission to call somebody that. A spacehead. Not dumbass. I mean, know your audience before you do that, I guess. I say that as I say the word dumbass for the 3rd time in 10 seconds here, but that's okay. So yeah, atoms are real small, and even smaller is the nucleus. So very strange that something like this could exist in this sort of format. In fact, this was a puzzle that took until about 1920 or so. I want to say 1920, 1910s, 1920s, whenever Rutherford did his experiment, for them to figure out, oh, atoms aren't solid spheres. They're just little teeny tiny little dots that exist in this sort of realm of electronic effect, I guess we'll say, of charge. All right. Now, what is the nucleus? What exactly is the solid part of the atom? We'll show that, I guess, in a second here. Where do I show that? I guess I talk about that in the next section. Okay. Anyway, we're going to talk about the parts of the atom in section 7.2, which we'll get to before we stop today. All right. Now, atomic matter makes up everything in the universe. And of the atomic matter present, we can divide it into up to 118 different types. And those are the elements on the periodic table that I showed you earlier. Do I still have that handy? I fell asleep, but I can recapture it. P table. Boop. All right. So again, these are the 118 different types of elements that are present on our periodic table at P table, and these are the ones that we are aware of in the universe. Now, more could exist. There could be an element 119. It has not been detected or observed yet, at least as far as I am aware. Now, we discussed this on the first day, where I dropped a bunch of elements in water, and we saw things explode. And we saw that no matter who did the sodium experiment, you got the same result. The conclusion that we would draw here is that for a given element, all of the atoms of that element must behave the same way in terms of chemistry. So if I'm looking at sodium, and sodium explodes when you put it in water, then all sodium will behave the same way. Because it's sodium, it has the exact same structure, it will have the same outcome when exposed to the same conditions. So all sodium atoms will explode in water. Now, if you combine atoms, oh, excuse me. If you combine atoms together to get a molecule, the compound that you get will be a uniquely identifiable substance with a given formula. Now, these formulas will always have whole numbers. So, for example, here are two formulas here, H2O and H2O2. But what you will never see is H2O 1.5. That's not possible. You cannot have a part of an atom. You can only have whole numbers. Now, these two things are very different. If you drink water, it's refreshing and healthy for you. But if you drink H2O2, you will die. And I don't have the sound effect queued for it, unfortunately. And the reason for that is H2O2 is extremely reactive. This hydrogen peroxide, if you pour that on anything, it bubbles and fizzes and basically dissolves or reacts or kills whatever it's interacting with. So we use it as a gargle for mouthwash, but we use it super dilute. Only 3% of what you consume is actually hydrogen peroxide. And the difference is how those atoms are bonded together. We're going to talk a little bit about bonding later, and then we'll cover it in much more detail in 161. All right. Now, the act of mixing different types of atoms together to form new substances, that's chemistry. So if you mix substance A and substance B together, you may form a new substance. For instance, if I put sodium metal and chlorine gas together, I get table salt. This is where table salt came from. First, sodium metal was formed and chlorine gas was formed at the start of the universe. And then they collided with each other, and we formed table salt out of it. And then it all ended up in the ocean. Now the ocean is super salty about it. Saltier than a Twitch gamer. Now, atoms aren't pieces that we can disassemble easily. Atoms are pretty much just there. So if I give you a sodium atom and you want to do chemistry with it, you can't take it apart and make it into, say, a hydrogen or a helium or something like that. It doesn't work like that. Atoms are essentially indestructible. You cannot break them into single pieces when you're doing chemistry. Now, that's not to say that you can't do this at all. In fact, there's a lot of research that's going on in particle colliders in places like CERN in Switzerland, where we accelerate atoms to extremely high speeds around a track, and then we collide them into other things. And then we observe what happens. And in the observations, maybe we made new stuff or we found different fragments or something cool like that. And so that's called nuclear chemistry. We're going to talk about nuclear chemistry a little bit in 163. But for the most part, we're going to ignore that nuclear chemistry is a thing that happens because it's way too high energy for us to really consider. We're going to do chemistry, which is stuff that happens at room temperature. Now, this is sort of a preview for what we're going to be talking about in later units. I believe this is 9 and 10. Whenever I say believe, it's because we changed all the numbers recently, and I never remember the old, or I remember the old system, but not the new one. We're going to talk about molecular and ionic compounds. We're going to spend a lot of time on ionic compounds and then a little time on molecular compounds. And then we'll do the same thing again next quarter. But molecular compounds are independent entities of bonded atoms. So I'm circling here a collection of water molecules. And you'll notice that when I draw the red line, I can completely encapsulate the water molecule because it's not actually connected to other water molecules. So molecules or molecular compounds are independent things that just sort of shuffle about. Virtually all liquids that we encounter in our daily lives are molecular. And they consist of water molecules and other molecules bouncing around kind of like you're at a crowded pub or bar. You know, back when we could do that. Although we're starting to be able to go out to bars now. It's kind of nice, actually. Or restaurants or what have you. If you're in a crowd, you're not physically stuck to all of the other people that you're trying to make your way through. If you're trying to get your way to the service counter so that you can place an order for nachos or whatever, and you have to push your way past 30 other people, the state that you're moving through is kind of like a liquid, but you're still independent of those other people. That's how molecules exist. Molecules are all independent. Ionic compounds would be if all of the people were chained together with shackles. These individual atoms that are here, they're actually ions because they have charges, but we'll talk about ions a little bit later. These are all stuck together by a specific force. And this force propagates in 3 dimensions to hold the stuff together into a solid shape. And I'm trying to draw it in 3D as best I can here. There we go. And so we don't form a molecule. Instead, what we form is called a lattice. And a lattice is just a crystalline sort of object that is not independent. Now, if you heated this up a lot, like to, say, 1,000 degrees Celsius, you could actually get this to melt and fall apart. But at room temperature, these ions are stuck here. So, an ionic compound is basically a repeating pattern of atoms that are charged called ions. And they're stuck together in this pattern over and over and over and over, virtually forever. You eventually reach the edge of the lattice, which is this cubic shape that you can see in the diagram right here. So those are the 2 types of molecules or compounds that we're going to be looking at. Molecular compounds are independent structures that exist individually. Ionic compounds do not. They are all stuck together in one giant macro, I want to say macro molecule, but it's not really a molecule. In one macro lattice, I guess we'll say. In fact, it turns out that matter very rarely exists as independent atoms. Noble gases can do this. We're going to talk about what the noble gases are later. But these elements, helium, neon, argon, krypton, xenon, radon also does too. They all exist as independent atoms bouncing around as gases. But the vast majority of matter exists as molecules. And those molecules exist in the molecular state like we described on the previous slide. I have some pictures here that show some various atoms. You'll notice that they are color-coded, and this color coding is a standard. For example, the white atom is always intended to be hydrogen. It's also represented as slightly smaller, because hydrogen is the tiniest atom. Actually, that's not technically true. Helium is technically smaller, but hydrogen is the tiniest bonding atom, we'll say. There we go, that's true. Oxygen is depicted as red because fire, I guess. Oxygen is a necessary component of fire. I don't know why they chose yellow for... Oh, I know why they chose yellow for sulfur. Sulfur is yellow. Orange for phosphorus, not sure about that one, though. Carbon is black, typically, and that's because carbon typically exists as substances that we perceive as black. For example, coal, or charcoal, or... I just said the same thing twice. Graphite, what we use as pencil lead. Those are all forms of carbon, and they're all black. They absorb light very effectively. Other atoms have different colors. For example, nitrogen is blue. This is not something you have to commit to memory, but it is something that you will just pick up as you progress through the chemistry series. All right, this last activity that we're going to do for this section, we're going to try and categorize molecules using different labels. And the first label that we're going to use is a number label. We're going to use a numeric prefix to describe the number of atoms in a molecule as either monatomic, mono meaning one, diatomic, di meaning two, and so on. So we got triatomic, tetraatomic, pentatomic, and so on. Typically speaking, the term polyatomic is used for more than 3 atoms, because at that point, like, why bother? There's a lot of atoms there. That's fine. So we can categorize a molecule based on the number of atoms that are in there and give it one of these labels. And then we can give it a label based on the types that are present. Is there only one type, which would be homoatomic, or are there different types, which would be heteroatomic? So those are the different categories of labels. You have a number label and a type label. And your task for these molecules is to assign both labels to each molecule. Now, this is intended to be 3 different pictures and 3 different formulas, but they are not related to each other. So this is, we'll say number 1, 2, 3, 4, 5, 6. When I didn't have the grid, everybody thought that, like, they correlated with each other, and then I put the grid in and people still did, so it's like, oh, whatever. So these are 6 different problems. The top 3 are models. I want you to apply labels to them. Type your answer in the chat. Then I want you to try and do that with the written out formulas at the bottom. Apply labels to those too. While you're doing that, Maya will meow at you. I don't know if you heard her, but that's okay. All right. And I'm going to hit mute. I'll give you a few minutes to do that. We'll go over the answers, and then we'll be about ready to call it a day, it looks like. So we'll do the rest of Chapter 7 next week. Go ahead and do these examples, and I'll be back in a little bit. All right, I'll give you 1 more minute or until Maya gets off my lap because she wanted to say hi. All right. She got off my lap only to immediately come back on the lap. So, here, let me move the mic and you can walk on my lap. Maya, don't step on the cord. Maya, you gotta move your paws. I cannot work under these conditions. Maya, gotta move. There you go. All right. So I have a cat on my lap. I'll do the best I can here. Oh, I'm already off to a great start here. All right. So for number 1, we've got 3 that are all the same color. So this must be homoatomic. And there's 3 atoms, so this is triatomic. For the second one, I've got 4 atoms that are red, but then I have 1 blue one. So this is heteroatomic and polyatomic because there are more than 3. You could also say pentatomic, that's fine. If you have 1 atom by itself, it can never be anything other than monatomic and homoatomic, right? In fact, this is kind of redundant, but you could include it anyway. That's fine. So if you did include that, that's okay. If you didn't, also okay. It's just because how could it be heteroatomic, right? Down here, there are 12 total atoms, right? How do you know that there are 12 total atoms? Well, there's 6 carbon and 6 hydrogen. And so this would be polyatomic. And then how many different elements are there? Well, there's 1, 2. So this is heteroatomic. There's 2 atoms in this Br2 molecule. So this would be diatomic. And because they're both bromine, this would be homoatomic. And then finally, there's 3 atoms here. So this would be triatomic. And because they're different types, heteroatomic. And there you go. So that's how we categorize molecules. All right, any questions, let me know. I believe that's all we're going to do today because this next part will be, again, longer than 10 minutes. So we're going to leave it at that. I do want to thank everybody for coming out to the lecture. Tomorrow we're going to go over lab worksheet number 2. And we're also going to have a Q&A. So please show for that. Lab number 2 is much more work than the first one. I realize that the first lab is a very, like, Babby's first lab sort of thing. The second one is much more difficult in terms of complexity and also what you have to do. And it's all math. So we're going to talk about it in more detail tomorrow. So tune in for that. Thanks for watching. I don't have the audio queued up for the outro, so I got to go quickly get that. I should really just leave it open, but I did reboot the computer so that everything would work. All right, that's all I got. So have a wonderful rest of your day, and I will see you tomorrow for the review and the lab discussion. Make sure you get quiz number 2 done. It is due tonight, and we'll close tomorrow. Take care.